Today, we continue our exploration of information by talking about encoding, the very important concept called entropy, and then we'll talk about a specific type of encoding called Huffman coding. In the previous video, we talked about a tree, and we said you could make a yes-no decision, followed by another yes-no decision, followed by yet another yes-no decision. So in 3 levels, in asking 3 yes-no questions, you could determine 8 things. And we said 2 to the 3, where 3 is the number of questions that we asked, is equal to 8. Or if you prefer, we could talk about this being the message space. With 3 questions, we are able to uniquely identify 8 different items. Let's illustrate what we mean by unique items by using a bag of candy. Think of this bag of candy as a random symbol generator, where the color is the symbol. For example, there's our first color, it's green. If it gives us another symbol, blue, yellow, and orange. If we go back to our decision tree, we could say that this is brown, red, orange, yellow, green, and azul. If we were to put this in tabular form, we would talk about the symbol, and then we could talk about the encoding. We'll start with brown. That's this path here as 0, 0, 0. Red is this path, 0, 0, 1. Orange is 0, 1, 0. Yellow as 0, 1, 1. And so on and so forth. So that's 1, 0, 0, and 1, 0, 1. This type of encoding is known as fixed. It's fixed in that we always ask the same number of questions. Is it brown? And the way we'd ask that question, we would say, is it 0? Is it 0? Is it 0? And that's how we walk down this tree to determine that it's brown. Or if it's orange, we ask 3 questions, 0, 1, 0. Suppose I gave you this number sequence, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. From there, could you determine what the color sequences were? We'll assume that this is what's called the most significant bit, and we just look up our table. So that's this one right here. So that would be green. That would be red. Let's see, 0, 0, 0 is brown, and 1, 0, 0 is green. So we used 3 yes-no questions, 3 bits to determine which symbol we were talking about. Make a note to yourself, this fixed width encoding is fine, but we can do better. For example, we know that the message space is only 6. So 2 raised to the n is equal to 6. So we can ask ourselves, how many questions on average would we need to ask to determine what color it is? Solving for n, we would say, let's see, so log 6 divided by log 2. This would suggest that on average, we'd have to ask 2.585 questions per symbol. So we'll write that as bits per symbol. And that is, of course, assuming equal probability for each symbol. Speaking of probability, there is another way we can talk about information. So information is equal to log base 2 of 1 over the probability that a particular symbol will occur. So we can say this is information, and this is the probability of that particular symbol. We assumed, let's see, 1, 2, 3, 4, 5, 6. We assumed 6 symbols, and if we assumed equal probability, that means the probability of any particular symbol is 1 over 6. So the probability in this case is about 16.7% for any particular symbol. So the information is then log base 2 of 1 over the probability. Solving for I, that would be log of 0.1, 6 repeating, invert, divided by log 2. And there we are. So that's 2.585 bits per symbol. Okay, so on average, we would have to ask 2.585 questions. And you'll notice that this here is the same as our calculation here. Be sure to add that to your note card. Now, we made an assumption in all of this, which is we assumed equal probability for each of the symbols. You have to ask yourself if that's true. That brings us back to our symbol generator. What is the nature of the symbols that it gives us? Do they have equal probabilities, or are they unequal, with some symbols more likely to occur than others? Well, just looking at it, in this particular case, it looks like we have many more green than anything else. Now that we have all our symbols laid out, I believe there's 6 of them, 1, 2, 3, 4, 5, 6. There we go. Remember that color is the symbol of interest. And you have to ask yourself which color or which symbol contains the most information. And if we look at it, it's right here. So the information is log base 2 of 1 over the probability. And if you were to solve that, you would find that red, the one with the lowest probability, carries the most information. And the reason for that is because it's the one that you have to ask the most questions about. Let's look at it this way. If I were to take all these candies and put them back in the bag, but you knew what the probabilities were, would you ask me if the question was red? The answer is no, because you would be much better off asking, is it green? Because most of the time, if you asked if it's green, you would be right. So instead of asking a whole bunch of questions, you could ask one question, and chances are you would be right on the first question. Therefore, on average, you have to ask less questions. Let's look at this a different way. Let's add some symbols. Here's the occurrence of that symbol. So let the symbols be A, B, C, D, E, and F. And as far as occurrence goes, 104 for type A, 10 for B, 22, we'll say 20, 14, and 30. So how many occurrence or how many symbols did we have? And if we add those up, that should equal 200. From there, we can determine the probability of the ith symbol. If we work that out, that would be 104 divided by 200 gives us a probability of 0.52 for symbol A. 10 divided by 200 for symbol B. And we can just continue on. If we add up all of the probabilities, that should equal 1. We can now calculate the information per symbol, which we defined up here as log base 2 of 1 over the probability. So that's log of 0.52 invert divided by log base 2. 0.943. So for the symbol A, on average, it's 0.943 questions or bits for that particular symbol. For symbol B, it's log 0.05 inverse divided by log of 2. You can see you need to ask many more questions for symbol B because it has a much lower probability of occurrence. Remember that this is the information per symbol. If we add another column, we can talk about the information for all of those occurrences. For symbol A, it's 104 because we have 104 occurrences of that symbol multiplied by 0.943. That's 98.1 questions that needed to be answered to determine symbol A. For symbol B, it's 43.2. Now, if we add all these together, so it's 98.1 plus 43.2 plus 70 plus 33.2 plus 53.7 plus 121. For all of these together, we would had to have asked 419.2 questions. Notice that there are 200 symbols, so we can just divide this number by 200, and that is the average number of questions that needed to be asked to solve this. Let's move to a spreadsheet to make this more clear. There's our symbol A, B, C, D, E, and F. The occurrence, we said 104, 10, 22, 20, 14, and 30. If we take the summation of all of these, it should be 200, and it is. This column is the probability of the ith symbol. That equals this divided by 200. Copy that down. Next is the information associated with the symbol. That is log of 1 divided by this cell divided by log of 2. So on average, this is the number of questions that need to be asked to determine each symbol. From there, we determine the total information for each symbol. For example, for symbol A, there were 104 occurrences. Each occurrence contained 0.94 bits of information. So total info equals that cell by this. We drag that down. If we take the summation of this column, we see that we asked 413 questions to identify all 200 symbols. So the final thing we want to do is take that number, so this number, and we divide it by 200, which is the number of symbols that occurred. This is the entropy of that particular system. Given these probabilities, this is the measure of information contained in the set. On average, we ask 2.07 questions to identify each symbol. For some symbols, we only have to ask one question. Is it A? And chances are, a little more than 50% of the time, you would be correct. Is it A is a very good question to ask. Some symbols take many questions. For example, to find out if it's B, you typically have to ask 4 questions. Let's look at this again on the Scratchpad. There was the symbol. There was the occurrence. There was the probability of that particular symbol, the probability of the ith symbol. Next was the information per symbol. Then there was the total information. For symbol A, it occurred 104 times. The probability was 104 over 200. The information contained per symbol was log base 2 of 1 over the probability. So that was 0.943. And the total information was a multiple of the occurrence by the information per symbol. So that was 104 by 0.943. And we did that for each symbol. When we were finally done, we said that was 414 questions or bits. And because there was 200 occurrences, we called the entropy H as 414 divided by 200. Therefore, this particular set, we had to ask 2.07 questions or bits per symbol. There is a shorter way to calculate entropy. Entropy, H, is equal to the summation. We'll start at the first symbol and go to the nth symbol. Then we're going to take a weighted average of the information of each symbol. We recognize this as the information associated with the ith symbol. And then by multiplying it by the probability of that particular symbol, you end up with a weighted average. And what you do then is you multiply all of the symbols together. Back to our previous example, we had symbol A. It had a probability of 0.52. So in our column, we would say 0.52 log base 2 of 1 over 0.52, which would be log of 0.52 invert divided by log 2. So this here, oh, and then you multiply that by 0.52. Okay, so in this column, you would have 0.491. We'll start by copying this and pasting it. We can hide this column because we're not interested in the occurrence anymore once we have the probability. Now for the equation, we take the probability and we multiply by log of 1 divided by this cell divided by log of 2. We copy that, and then we add these together. There we are, which is the same answer as we got here. So the entropy using the long method is 2.07, and it's the same here. Personally, I like this method better because there's less room for error. Let's do the calculation for symbol B while we're here. So B had a probability of 0.05. So take this 0.05 log base 2 of 1 over 0.05. For the calculator, that's 0.05 times log of 0.05 inverse close, divided by log 2. So that's 0.216, which is the same as we had for our spreadsheet calculation. Again, I'll leave it up to you to fill this out for the rest of the symbols. And in the end, you should arrive at 2.07 bits per symbol. Again, that is entropy, which is to say that is the absolute least number of questions that you would need to ask in order to determine what all 200 symbols were. With that said, we have to go way back to the beginning of our discussion. Remember when we started, we introduced the symbols and we used something called fixed encoding. And with that, we declared that we had to ask 3 questions. We asked 3 questions. Every single time there was a symbol, we had to ask 3 questions to determine what the color is. But that's no good, because we know that the information would suggest that we only have to ask 2.07 questions. This has some serious implications when we send this over a channel. If we were to use fixed width, we'd have to ask 3 questions. We'd have to send 3 bits over the wire. Whereas the measured entropy suggests we could ask as little as 2.07 questions per symbol. What we need to do now is find a method to encode that is approaching entropy. By the way, you can never get better than entropy, because if you get better than entropy, that means you've lost information. What we're going to do now is something called Huffman encoding. Now there's a lot to it, but we'll just use it as an algorithm for our purposes. Step 1, we want to order by decreasing probabilities. 0.52 for A, and I believe F was 0.15. C was next. Then there was D, and then E, and finally B. Step 2, we're going to build a tree. And what we're going to do is we're going to join those items with the lowest probability. So looking at our numbers, we see that E and B have the lowest probability. So here is E, and here's B. And if we add those probabilities together, so 0.07 and 0.05, we would see that that's 0.12. And we'll cross those off the list. 0.12 is greater than C, which is 0.11, or D, which is 0.10. So that means we're going to join C and D. Same thing we did before. We're going to add the probabilities together. So 0.21, that takes care of those. The next 2 lowest are the join of E and B and F. So we'll take this and we'll put F here. So 0.12 plus 0.15, 0.27, so that takes care of F. Now we look at A, which is 0.52. That's still the greatest, which means we're going to join these 2 because they have the lowest probability. So 0.48. And finally, we can join A. And that should give us a total of 1. This is similar to the decision tree we made before, except now it's not symmetrical. Just like that tree, we're going to add the symbols, so 0 and 1. So most of the time, the question we ask is it A? And we ask that question with a 0. Again, we'll add in the other numbers as before. And now we can talk about the encoding. So the symbol A is encoded as 0. The symbol B is this tree here, so it's 1, 1, 0, 1. The symbol C is encoded as 1, 0, 0. D is encoded as 1, 0, 1. E as 1, 1, 0, 0. And finally, F as 1, 1, 1. So here we have variable width encoding. And this is where things become really interesting. For example, if you were sent this sequence of numbers, could you decode it? The answer is absolutely. So we start here on the left. So that's an A. Do a different color here. So there's an A. There's another A. So 1, 1, 1. That's an F. A. 1, 0, 0 is a C. A couple more A's. And let's see the last one. 1, 1, 0, 1. That's a B. So here we've encoded our system now using variable width encoding. If we go back to our original spreadsheet here, we can talk about the encoding. So the symbol A was encoded as 0. B was encoded as 1101. C as 100. D as 101. E as 110. Whoops. 1100. And F as 111. Now watch this. How many bits were used in the encoding? The answer is 1 bit there, 4 bits there, 3, 3, 4, and 3. So to determine if it was a B, we had to ask 4 questions. To determine if it was A, we had to ask 1 question. Now, how many bits were used? So if we multiply the occurrence by the number of bits, we can see that we had to ask 104 questions to determine our A's. If we carry this down or copy this down, we add all of these up with Huffman encoding, this is how many questions we had to ask. To determine this sequence for this 200, we had to ask 416 questions, which means Huffman encoding is this divided by the number of symbols. When all is said and done with Huffman encoding, we had to ask 2.08 questions per symbol. And that is very close to the entropy. So for this particular set, Huffman encoding worked out very well. So looking back, we determined that the entropy was 2.07 bits per symbol. And we determined that with Huffman encoding, we could achieve 2.08 bits per symbol. And that is much better than our original fixed width encoding, where we had to ask 3 questions per symbol. We should make a note here that entropy is always going to be less than or equal to the encoding. In fact, you could think of entropy as a theoretical limit. In order to get your message across, you have to transmit the whole message. Entropy describes how many questions or how many bits you had to use to achieve that goal. Know that there are times when it's okay to lose information, but that's a topic for another day.